This presentation is delivered by the Stanford Center for Professional Development.
Okay, let's get started. Welcome to Intro to Robotics 2008. Well, Happy New Year, everyone. So, in Introduction to Robotics, we are going to really cover the foundations of robotics. That is, we are going to look at mathematical models that represents robotic systems in many different ways. And in fact, you just saw those in class. You saw a simulation of a humanoid robotic system that we are controlling at the same time. And if you think about a model that you are going to use for the simulation, you need really to represent the kinematics of the system. You need also to be able to actuate the system by going to the motors and finding the right torques to make the robot move. So let's go back to this. I think it is quite interesting. So here is a robot you would like to control. And the question is, how can we really come up with a way of controlling the hands to move from one location to another? And if you think about this problem, there are many different ways of, in fact, controlling the robot. First of all, you need to know where the robot is. And to know where the robot is, you need some sensors. So what kind of sensors you would have on the robot to know where the robot is? Any idea? GPS? Okay. Well, all right. How many parameters you can measure with GPS? Oh, that's fine. I mean, we can try that. How many parameters you can? What can you determine with GPS? Yeah, you will locate X and Y for the location of the GPS, right? But how many degrees of freedom, how many bodies are moving here? When I'm moving this, like here, how many bodies are moving? So how many GPS you want to put on the robot? You will need about 47 if you have 47 degrees of freedom, and that won't work. I mean, it will be too expensive. Another idea. We need something else. Encoders, yeah, encoders. So encoders measures 1 degree of freedom, just the angle. And how many encoders we need for 47 degrees of freedom? 47. Now, that will give you the relative position, but we will not know whether this configuration is here or here, right? So you need a GPS to maybe locate one object and then locate everything with respect to it. Or any other idea to locate? Yeah, by integrating from an initial known position or using vision systems to locate at least one or two objects. Then you know where the robot is, and then the relative position, the velocities could be determined as we move. So once we located the robot, then we need to somehow find a way to describe where things are. So where is the right hand, where is the left hand, where? So you need, what do you need there? You need to find a relationship between all these rigid bodies so that once the robot is standing, you know where to position, where the arm is positioned, where the hand is positioned, where the head is positioned. So you need something that comes from the science of... Well, I'm not talking now about sensors. We know the information, but we need to determine a model, the kinematic model. Basically, we need the kinematics. And when the thing is moving, it generates dynamics, right? So you need to find the inertial forces, you need to know. So if you move the right hand, suddenly everything is moving, right? You have coupling between these rigid bodies that are connected. So we need to find the dynamics. And once you have all these models, then you need to think about a way to control the robot. So how do we control a robot like this? So let's say I would like to move this to here. How can we do that? The hand, I would like to move it to this location. I'm sorry?
Forward or inverse kinematics?
Oh, very good. Well, the forward kinematics gives you the location of the hand. The inverse kinematics give you, given a position for the hand that you desire, you will be able to solve what joint angles you have. And if you do that, then you know your goal position angle for each of the joints. Then you can control these joints to move to the appropriate joint positions, and the arm will move to that configuration. Well, can you do inverse kinematics for this robot? It's not easy. It's already difficult for 6 degrees of freedom robot like an arm. But for a robot with many degrees of freedom, so suppose I would like to move to this location here. There are infinite ways I can move there. And there are many, many different solutions to this problem. In addition, a human do not really do it this way. I mean, when you're moving your hand, do you do inverse kinematics? Anyone? No. So we will see different ways of, I will come back to this a little later, but let's, I'm not sure, but the idea about robots is basically was captured by this image. That is, you have a robot working in an isolated environment, in a manufacturing plant, doing things, pick and place, moving from one location to another without any interaction with humans. But robotics over the years evolved, and today robotics is in many different areas of application. From robots working with a surgeon to operate a human, to robot assisting a worker to carry a heavy load, to robots in entertainment, to robots in many, many different fields. And this is what is really exciting about robotics, the fact that robotics is getting closer and closer to the human. That is, we are using the robot now to carry, to lift, to work, to extend the hands of the human through haptic interaction. You can feel a virtual environment or a real environment. I'm not sure if everyone knows what is haptics. Haptics comes from the sense, a Greek word that describes the sense of touch. And from haptics, so here is the hands of the surgeon, and the surgeon is still operating. So he is operating from outside, but essentially the robot is inserted, and instead of opening the body, we have a small incisions through which we introduce the robot, and then we do the operation, and the recovery is amazing. A few days of recovery, and the patient is out of the hospital. Teleoperation through haptics or through master devices allow us to control. So here is the surgeon working far away, operating or operating underwater or interacting with a physical environment in homes or in the factory. Another interesting thing about robotics is that because robotics focuses on articulated body systems, we are able now to use all these models, all these techniques we developed in robotics to model human and to create sort of a digital model of the human that can, as we will see later, that can be simulated and controlled to reproduce actual behavior captured from motion capture devices about the human behavior. Also, with this interaction that we are creating with the physical world, we are going to be able to use haptic devices to explore physical worlds that cannot be touched in reality. That is, we cannot, for instance, go to the atom level, but we can simulate the atom level, and through haptic devices we can explore those worlds. Maybe the most exciting area in robotics is reproducing devices, robots that look like the human and behave like life, animals or humans. And a few years ago I was in Japan. Anyone recognize where this photo is?
Osaka.
He said Osaka. But very good, but you are cheating because you were there. So this is from Yokohama, and in Yokohama there is Robotics. Robotics brings thousands and thousands of people to see all the latest in robotics. This was a few years ago, and you could see Asimo here. Asimo, which is really the latest in a series of development at Honda following P2 and P3 robots. And in addition, you could see, most of the major players in robotics, in humanoid robotics. Anyone have seen this one? Do you know this one? This is the Sony robot that actually, I think I have a video. Let's see if it works. The Sony is balancing on a moving bar, and this is not an easy task. And you can imagine the requirements in real-time control and dynamic modeling and all the aspect of this. And this was accomplished a few years ago. Well, actually, we brought this robot here to Stanford a few years ago, and they did a performance here, and it was quite exciting to see this robot dancing and performing. There are a lot of different robots, especially in Asia, Japan and Korea, humanoid robots. AIST built a series of robots, HRP 1, 2, and they are building and developing more capabilities for those robots. One of the interesting show that we had recently was near Nagoya during the World Expo in Aichi, and they demonstrated a number of projects. Some of them mainly came from research laboratories that collaborated with the industry to build those machines. This is a dancing robot. Let's see. This is HRP. So HRP is walking. Walking is now well mastered, but the problem is how can you move to a position, take an object, and control the interaction with the physical world. This is more challenging. You see the sliding and touching is not completely mastered yet. But this is the direction of research in those areas. This is an interesting device that comes from Waseda University. This robot has additional degrees of freedom that... Okay, another problem now? Okay. So you have additional degrees of freedom in the hip joints to allow it to move a little bit more like a human. Let's see. Oh, this is one of my favorite. This is a human-like and human-like actuation in it. So artificial muscles that are used to create the motion. But obviously, you have a lot of problems with artificial muscles because dynamic response is very slow, and the power that you can bring is not yet. But we will talk about those issues as well. Okay, let me know what you think about this one. Just I keep silent. So what do you think? Do we need robots to really have the perfect appearance of a human, or like we need the functionalities of the environment? Like if we are working with the trees, we specialize the robot to cut trees. If we are working in the human environment, then we will have a robot that has the functionalities of 2 arms, the mobility, the vision capabilities. So these are really interesting issues to think about, whether we need to have the robot biologically based or functionally based, and how we can create those interactions in an effective way. Last one I think is, this is an interesting example of how we can extend the capabilities of human with an exoskeleton system. So you wear it and you become a Superman or a Superwoman, and you can carry heavy loads. They will demonstrate here carrying, I believe, 60 kilograms without feeling any weight, because everything is taken by the structure of the exoskeletal system you are wearing. Another interesting one is this one from Tokyo Institute of Technology, a swimming robot. So make sure no water gets into the motors. Anyway, the thing is, robotics is getting closer and closer to the human, and as we see robots getting closer to the human, we are facing a lot of challenges in really making these machines work in the unstructured, messy environment of the human. When we were working with robots in structured manufacturing plants, the problems were much simpler. Now you need to deal with many issues, including the fact that you need safety. You need safety to create that interaction, and this distance between the human and the robot is very well justified. You don't want yet to bring the robot very close to the human, because these machines are not yet quite safe. Well, the development in robotics has many aspects and many forms, and really at Stanford we are fortunate to have a large number of courses offered in different areas of robotics, graphics, and computational geometry, haptics, and all of these things. And you have a list of the different courses offered all along the year. And in fact, in my this is the Intro to Robotics. In spring, I will be offering 2 additional courses that would deal with experimental robotics, that is applying everything you have learned during this class to a real robot and experimenting with the robot, as well as exploring advanced topics in research, and this is in advanced robotics. So you realize I'm Asامة Khotib, your instructor, and you have this year, we are lucky we have 3 TAs helping with the class: Pete, Christina, and Shanning. So let's, they are over here. Please stand up, or just turn your faces so they will recognize you. And the office hours are listed, so we will have office hours for me on Monday and Wednesday, and Monday, Tuesday, and Thursday for the TAs. The lecture notes are here, and they are available at the bookstore. This is the 2008 edition, so we keep improving it. It's not yet a textbook, but it is quite complete in terms of the requirement and the things you need to have for the class. So let's see. The schedule, so we are today on Wednesday the 9th, and we will go to the final examination on March the 21st. There are few changes in this schedule from the handout you have, and we will update these later. There is these changes happen just in this area here around the dynamics and control schedule. But essentially what we're going to do starting next week is to start covering the models. So we will start with the spatial descriptions, we go to the forward kinematics, and we will do the Jacobian, and I will discuss these little by little. That will take us to the midterm. One important thing about the midterm and the final is that we will have review sessions, and the class is quite large, so we will split the class in two, and we will have two groups that will attend these review sessions, which will take place in the evening, and they will take place in the lab, in the robotics lab. And during those sessions, we will cover the midterm of past years and the finals of past years. And what is nice about those sessions is that you will have a chance to see some demonstrations of robots, and at the same while eating pizza and drinking some. So that will happen between 7 and 9. Sometimes it goes to 10 because we have a lot of questions and discussions. But these sessions are really, really important, and I encourage you, and I encourage also the remote students to be present for the sessions. They are very, very helpful in preparing you for the midterm and the final. So as I said, this class covers mathematical models that are essential. I know some of you might not really like, well, getting too much into the details of mathematical models, but we are going to really have to do it if we are going to try to control these machines or build these machines, design these machines. We need to understand the mathematical models, the foundations in kinematics and dynamics. And we will then use these models to create controllers, and we are going to control motions, so we need to plan these motions. We need to plan motions that are safe, and we need to generate trajectories that are smooth. So these are the issues that we need to address in the planning and control, in addition to the fact that we need to touch, feel, interact with the world. So we need to create compliant motions which rely on force control. So force control is critical in creating those interactions, and we will see how we can control the robot to move in free space or in contact space as the robot is interacting with the world. And then we will have some time to discuss some advanced topics, just introduce those advanced topics so that those of you who are interested in pursuing research in robotics could make maybe plans to take the more advanced courses that will be offered in spring. So let's go back to the problem I talked about in the beginning, the problem of moving this robot from one location to another. Suppose you would like to move this platform. This is a mobile manipulator platform. You would like to move it from here to here. How do we do that? Well, we said essentially what we need to do is somehow find a way of discovering a configuration through which the robot reaches that final goal position. And this is one of them. You can imagine the robot is going to move to that configuration. But the problem with this is the fact that if you have redundancy, so what is redundancy? Redundancy is the fact that you can reach that position with many different configurations because you have more degrees of freedom in the system. And when you have redundancy, this problem of inverse kinematics becomes really difficult problem. So, but if you solve it, then you will be able to say, I would like to move each of those joints from this current position, this joint position, to this joint position. So you can control the robot by controlling its joint positions and by creating trajectories for the joints to move, and then you will be able to reach that goal position. Well, this is not the most natural way of controlling robots, and we will see that there will be different ways of approaching the problem that are much more natural. So to control the robot, first you need to find all these position and orientation of the mechanism itself, and that requires us to find descriptions of position and orientation of object in space. Then we need to deal with the transformation between frames attached to these different objects, because here, to know where this end effector is, you need to know how, if you know this position of those different objects, how you transform that descriptions to find finally the position of your end effector. So you need transformations between different frames attached to those objects. So the mechanism that is the arm in this case is defined by a rigid object that is fixed, which is the base, and another rigid object that is moving, which we call the end effector. And between these two objects, you have all the links that are going to carry the end effector to move it to some location. And the question is, how can we describe this mechanism? So we will see that we are using joints, different kinds, joints that are revolute, prismatic, and through those descriptions we can describe the link, and then we can describe the chain of links connected through set of parameters. Don't worry, Denevit and Hartenberg were two PhD students here at Stanford in the early 70s, and they thought about this problem, and they came up with a set of parameters, minimal set of parameters, to represent the relationship between two successive links on a chain. And